Hello, everybody. So today I'm making a video about dilution factor and the math behind it because I know it could get really confusing. So I'm gonna go ahead and share my screen. This was a little drawing that I made up last semester, and I feel like it kind of outlines things a little bit better. So let's first focus on the actual factor itself. So uh, if you aren't familiar with scientific notation, um, the math behind it is that you're multiplying 10 by itself, however many times that the exponent expresses. So if we put 10 to the third, that's going to be 10 times 10 times 10. So that's going to be 1,000. Um, I know a lot of people think about it this way. They think, okay, um, 10 to whatever power is that number of zeros. So if I'll use 10 to the third again, then I said it was 1,000. That has 3 zeros. That's how people think of it. So dilution factor is the positive exponent that's expressed. It's always going to be a very large number. Now, the dilution, how we express how far we've diluted something, it's always going to get smaller, right? We take a more concentrated version and dilute it out. We're adding more water. At least in our lab's case, when we did the milk lab, that's what we did. We added sterile water. So that since that's going to be a much smaller number, we turn that into a negative exponent. So when it's a negative exponent, it's kind of reversed. So 10 to the negative third would be, bear with me, 3 in the thousandths place for decimals. Or it would be 1 in the thousandths place for decimals if it was to the negative third exponent. So we can kind of think about that as moving the decimal place 3 times over. So for our 1,000, if we put it in terms of the -3, we would just be moving it over, and it would look it would be 1 essentially. So if you want to see it this way, for the dilution ratio, it's 1 to 10 to the -3. Is that, I don't know if that makes sense, but it's always going to be a much smaller number. If you'd like to think about it this way, the ratio is always going to be 1 to the dilution factor or the negative exponent version of the dilution factor. And then also you can express it as a, here, I'll slide over here. You can express it as a ratio, which is in its like division form. It's, what is it called? I'm sorry, I can't think of the word, but it's, 1 over something. So that's how we calculate it, and that's how we can, flip it around. So a lot of people also get confused in terms of like, okay, well, we're taking this much and putting it in here. How is it still even? This over here, the final volume over initial volume, the initial volume is not the initial volume of the first test tube that we took from. It's going to be the initial volume of the sample we took. So if that initial volume was 0.5 milliliters and we put it into a 4.5 milliliter sterile water, just sterile water test tube, then the final volume of that whole thing is what we'll put for final volume. So 0.5 underneath 5 milliliters, that's going to give us our 1 to 10 to the -1. It should be 10 to the -1. So yeah, let's see. I know this math isn't as complicated as like the dilution factor and everything. But the more practice you get with it, the more comfortable you'd be. So if we hypothetically had 132 colonies, we have to ask ourselves, first of all, we're given a number of colonies. Is this within the 30 to 300 range? Yes, it is. So we're going to move on to the dilution factor, and we can put that in several other forms. It could be given to us in several other forms, but we would know that if it's 1 to 100,000 or 10 to the negative fifth, our dilution factor is going to be 10 to the fifth. So then in our mathematical equation here, we have 132 times 10 to the fifth CFUs per milliliters. Or if you want to put it into correct scientific notation, 1.32 times 10 to the seventh. But you see how I moved that decimal over? I moved it 2 places to the left, which means I added 2 exponents to my 10. And yeah, I just did a little rundown here of what that means. But yeah, it's not too complicated when you break it down. I think the biggest thing is that we just don't get a whole lot of practice in lab because it's more of a fundamental skill to be able to think in these terms. So if you would like a couple practice problems, I can probably write them up. Just let me know. Sometimes just hearing this a second time can help it click better. But you guys just let me know, and I will do my best to explain it or put it in terms that are more easily understood or give practice problems, whatever you guys need. So this was just a little bit of an example from class that we did the milk lab with. Everybody but the kefir group, which would have 2 more tubes, they saw this. You took your 5 mils and you kept on diluting it out. So the biggest thing I think that if people understand the dilution factors and ratios between test tubes, but they kind of get lost at the plate, the reason why it's considered another dilution is because the plate itself has volume. So if you want to think about the plate having 4.5 milliliters of volume, and that's another dilution, then think of it that way. That was like my biggest thing. I think when I was actually in the class, I was like, I understand the test tubes, but why the plate? Why is it another factor? So thinking about it in more volumetric terms can help out. Let's see. I believe that's about it in terms of the dilution factor and such. Again, if you have any questions, this is just kind of like a rehash type, thing. So questions are encouraged. If you think I glossed over something a little too much, let me know. But yeah, I hope this helps, and I'll see you guys around.